All right, so now we move on to lesson 9.2 part 2, and that's quadratic inequalities in one variable, specifically dealing with application or applications. Now, to start this lesson, what we're going to do is we're going to recap our algebraic approaches to solving these inequalities. So to start up, we're going to deal with one inequality, and we're going to deal with the different methods. Method 1, which is a non-algebraic approach, it's to graph the function or graph the inequality. For method 2, we're going to do our root and test point. And then method 3, we're going to do our case analysis, where method 2 and 3 are the algebraic approaches. And then the first one was our graphing method, which is non-algebraic. All right, now what we want to do with these is anytime we're given some sort of inequality, such as the one we're given above here, what we want to do is isolate it such that we have one side equal to 0. That's always step number 1 in this unit. So what I'm going to do is I'm going to take this original x squared minus 5x is less than, and let's just clean that up again, less than 3x squared minus 18x, and then plus 20. What we're going to do is we're going to subtract the x squared across, and we're going to add the 5x. If we do this to both sides, so we subtract the x squared plus 5x, we're going to get on the left-hand side that this is equal to 0. And then on the right-hand side, we're going to get 3x squared minus 1x squared is 2x squared. We're going to get 18x plus 5x is going to give us minus 13x. And then our constant term, because it's not going to be altered by any means, we're going to have this as positive 20 like this. Now, what we want to do is we want to factor this right away. As soon as we get it into this piece here, or we would want to factor it, in the case of graphing, we can actually go right into our graphing calculator and get our x-intercepts. So I shouldn't jump the gun right away because we're not doing an algebraic approach. We want it where this quadratic function or this quadratic is greater than 0. Now, in your graphing calculator, you're going to go y is 1 is equal to, we're going to put in 2x squared minus 13x, and then plus 20. Once we have this written down, now what we're going to do is let's pull this open in our graphing calculator. In our y equals function, or in the Casio, your graph function, we're going to go to 2x squared minus 13x, and then this is plus 20. Okay, we're going to graph it. Now, I'm going to put it under the standard window settings, and under the standard window settings, it looks like this. Now, what we're going to do is we're just going to figure out what the x-intercepts are by doing the second trace 0. So second trace 0 on the TIs for the Casios, it's going to be shift trace or shift G solve and then root. We're going to go left and right bound, and on the Casios, you won't need to go left and right bound, so don't worry about this. We find that the intersection point for this piece here is going to be where we have it at 2.5. So our first x-intercept, and we'll write that off to the side here, our x-intercepts are going to be where x is equal to 2.5. 2.5 as a fraction is actually 5 over 2, so I'll write it as an exact value here. Now, the other x-intercept, if we were to do this below or to the right here, x-intercept, we want to do this again, second trace 0 or shift G solve and root. We're going to go left bound, we're going to go right bound, and we're going to end up finding that our other 0 is at 4. So we're going to put x equals 4. Okay, now that we have the x-intercepts and we know what the general graph looks like, what I'm going to do is I'm just going to draw it roughly over here on the right-hand side. So let's see if we can draw a parabola that's kind of following this shape here. So it goes through at 2.5, comes back up at 4 like this, and it stoops just a little bit below. Perfect. This will do. Maybe not exact, but it will do. Now, because we're looking for where the inequality is strictly greater than 0, this means that these points are going to be hollow. So at these x-intercepts, I want you to draw hollow dots. And now what we're looking to describe is what are the x values such that the graph is greater than 0? And that would be located for up here and up here, meaning the x values we're actually searching for are going to be the ones we highlight in green here. Everything to the left of that point, or the left of the first x-intercept, and everything to the right of the x-intercept. Because we realize that the graph is above 0 here and above 0 here. These would go to infinity to the left and right. So any x value that's to the left of this first x-intercept or to the right will result in the graph being greater than 0. Now, the only other thing we'd want to put in the graphing piece here is we want to write in 5 over 2 and 0 representing our first x-intercept, and we'll just arrow to it. Our other one is going to be 4 and 0, and we would just want to write that in as 4 and 0 and then arrow down to it. Really important to make sure you're showing your x-intercepts on this graph, just because we don't really need a y-intercept or we don't need the vertex in this specific section of the unit or in inequalities in two variables like this, or in one variable, I should say. It is where we want to focus in on the x values that make it either greater than 0 or less than 0 or even equal to 0, but in this case, strictly greater than 0. So therefore, our solution would be the following. We would summarize this and say, therefore, the solution for where x squared minus, and this is 2x squared, I should make sure I include that, 2x squared minus 13x plus 20 is greater than 0 when either x is strictly less than 5 over 2, or we could even say and, when x is greater. And I'm just going to shift this over so that it all fits so we can summarize the solution all together. So there we go. When x is less than 5 over 2 and x is greater than 4. Now, what you should realize is that, again, from our previous lesson, if it's a strict inequality in the original inequality, then your answer will also have strict inequalities. That's a nice summary point there. We're going to highlight this and we're going to say that this represents the solution. So it just must be in these x intervals. So now we're going to go on to our first algebraic approach, which is the root and test point / sign analysis approach. What we have to do is we have to factor this original inequality, because that's what we would do. Is if we didn't know the roots, the x-intercepts, what we'd want to do is isolate it for one side being 0 like we did, and then factor it. So let's show those factoring steps just in the empty space we have here. So we're going to say 0 is less than the 2x squared minus 13x and then plus 20. Well, what things multiply to make 2 times 20, aka what things multiply to make 40 and add to make negative 13? We're going to find out that it would be 2x squared minus 8x minus 5x and then plus 20, because negative 5 and negative 8 multiply to make positive 40, but they also add to make negative 13. Now we're going to factor this by grouping. When we factor it by grouping, I can take out a 2x from the first, leaving me with x minus 4. And if I take out 5 from the second grouping, I have x minus 4. We see that we have a matching binomial, so I'm going to carry this up above and say 0 is less than. We take one of the common binomial. In this case, we take the x minus 4 and we write it in. And then we take our outside terms of 2x minus 5 and put them together. Now, from our quad equations unit, we know if we took each of these binomials and set them equal to 0 and isolated, we would figure out that x is equal to positive 4 and x is equal to 5 over 2 when we isolated these for 0 and solved for x. So our two x-intercepts match the ones that we found above, which is great. Now we want to be thinking about it in terms of the intervals. 5 over 2, which is 2.5, is less than 4, so we need to describe the following three intervals. The first interval is when the graph is to the left of x equals 5 over 2. So we're going to write this as x less than 5 over 2 for the first interval. The middle interval is going to be between these x-intercepts. We're going to write it as 5 over 2 is less than x, which is less than 4. So we want to test a point that's between the two x-intercepts. And then we want to test a point that's on the outside of these x-intercepts, aka x being greater than 4. Now let's pick some points to do that. Something that's less than 2.5, let's say 0, because 0 is an easy number to use. If it's between these two, 2.5 and 4, a value that's between those two is 3. And then the value I'm going to choose that's greater is just the next integer past 4. We're going to choose 5 there. Perfect. Okay, let's plug these into our binomials and see what they equal. So plugging this in, first and foremost, I plug in 5 over 2, and then this will be minus 4, bracket. We're going to end up having the 2x minus 5, or 2 times the 5. And I shouldn't be plugging in the x-intercept. I want to plug in the 0 value. So this is going to be 0 minus 4 times 2 times 0 minus 5, which is the second binomial. This is going to end up giving me negative 4 times negative 5. This gives me positive 20, and 20 is greater than 0. It's a positive value. Therefore, we would say that this is going to be something where the graph is above the x-intercept or x-axis. Now, if we test the point between, this is going to be 3 minus 4, bracket. We're going to have 2 times 3 minus 5 in a bracket. This will simplify to negative 1. 6 minus 5 is going to be 1. This gives us a value of negative 1, which is less than 0, meaning the end solution is negative here, or that the graph is negative in this region. or below the x-axis if we want to be more formal with it. Lastly, I'm going to plug in 5 for the brackets, so it's going to be 5 minus 4, close that bracket. For the next bracket, 2 times the 5 minus the 5 from the second bracket here. This is going to be 5 minus 4, which is equal to 1. 2 times 5 is 10, minus 5 is equal to positive 5. Therefore, end solution is 5, and that's greater than 0, aka the graph is positive or above the x-axis in this region. Now again, what did they ask for in this situation? They asked for where it is greater than 0. Where it's greater than 0 is in the following regions, in this region and this region. Now, how would we describe that as an inequality? We're going to say, therefore, in this case here, therefore, we had an inequality of 2x squared minus 13x plus 20 is greater than 0 when we have the following two cases. When either x was less than the 5 over 2, or, and you could even put and here, when x is greater than 4. I think and is better because it joins them together and says that these two are together as a solution, or makes it seem like it's just one or the other, which in this case it's not. We need to make sure both are in this here. Okay, now what I'm going to do is just move this over just so it's not like rubbing up against the edge of the paper here, and there's our solution. So it should match our graphical solution, which it does. Our algebraic approach matches the graphical solution, so therefore we know we're on the right track. Now the last example goes around or the last method I should say, is case analysis. And case analysis essentially is the same thing as root and test point or slash sign analysis. However, we just break it apart a little differently. And so here's how we're going to think about this. If we know that this inequality is where it's greater than 0, we have to list out a few different situations here. 2x squared minus 13x plus 20 is greater than 0. If this inequality is to be greater than 0, then if our first binomial is x minus 4 and our second binomial was 2x minus 5, and this has to be greater than 0, with this being in its factored form, in order for this to be greater than 0, either both the terms must be positive or both the terms must be negative in both these situations. As long as either of the binomials is both positive or they're both negative, you're going to end up getting something that is positive, or as we call it, greater than 0. So let's deal with case number 1. Case number 1, we're going to take these binomials and we're going to treat them separately and then look at them on number lines separately. So in this situation, we're going to write it as x minus 4 is greater than 0 and 2x minus 5 is greater than 0. If we were to isolate the x values here, we're going to add 4 to both sides. When we add 4 to both sides, we get x is greater than positive 4. For my second one, or my second inequality, we're going to add 5 across. When we add 5 across, we end up getting that 2x is greater than 5. We divide both sides by the 2 on each side, or the 2 that's attached to the x, and we get x is greater than 5 over 2. Now, we're going to summarize these on number lines. So I'm going to write one number line here, and then another number line right below it. There we go. Now what we're going to do is we're going to put these x-intercepts on there, where 5 over 2 is going to be the first x-intercept. So it will be the further left x-intercept. And then my more positive x-intercept, which is 4, will go on the right. We're going to describe these separately. So when x is greater than 4, again, we need to put a hollow dot, because a hollow dot represents that it doesn't actually include this, or it's not equal to this. And if it's greater than 4, we need an arrow that is going to the right. Okay, from here, if we know x is greater than 5 over 2, that means, again, it's going to be a hollow dot because it's not included, it's not equal to, but we're going to put an arrow that goes to the right. Now, here's what you should notice. We get a very specific region in which we have this overlap of the red lines overlapping one another. And if they overlap each other in this specific region, that means that it is part of the solution and that it represents a piece of the inequality or a part of the overall solution that we're going to need. Now, let's move on to case number 2. In case number 1, both of the inequalities were greater than 0, aka they were both positive binomials. Now we're going to talk about them in terms of making it greater than 0. They could also both be negative or less than 0. So for case number 2, let's go over and do that right off to the side here. We're going to write it as x minus 4 is less than 0 this time, and 2x minus 5 is less than 0. Now, isolating these, again, we're going to add 4 to both sides, just as we did in our previous inequalities. I'm going to write this as x is less than positive 4. For my other one, we're going to add 5, just as we did in the previous inequality, which will end up giving us 2x is less than positive 5. We divide both sides by the 2, and we end up getting that our x value is less than the 5 over 2. And I want to make sure that's a less than symbol, not some sort of bracketed term. Now let's write out our number lines for both of these. So we're going to put a number line here, and then a number line here. Excellent. And we just want to make sure there's the arrows on the end, representing that this is a number line that goes to infinity left and right. We're just like we did on the first one, we're going to put 5 over 2 first, because 5 over 2 is the smaller of the x-intercepts. We're going to put 4 over on the right-hand side. We're going to try and line them up all nicely so that they follow form together. There we go. Now, if x is less than this 4, then it has to be a hollow dot again, because it's not included, with an arrow that goes to the left. For my 5 over 2, it's also less than 5 over 2, so we want to draw an arrow to the left with a hollow point at 5 over 2. And just like we did with the first one, wherever these overlap, we want to make sure we highlight them, or that we draw a box around them, just to be like, hey, this is the solution region that should be included. Now, here's where we summarize our answer all together. We're going to do this right below. So therefore, we're going to say the combined inequality, or the original function, or the original inequality, which was 2x squared, and maybe I'll zoom in just to make this a little bit neater here. So this is 2x squared minus 13x plus the 20 is greater than 0 when the following happens. We clearly see that as long as it's greater than 4, they overlap. So therefore, that should be part of the solution. I'm going to write where x is strictly greater than 4. And then we also see that if, as long as it's strictly less than 5 over 2, they also overlap, meaning that's also part of the solutions. So I'm going to say x is greater than 4, and where x is strictly less than 5 over 2. If we're in any of those intervals of x, we end up having a solution, or we end up having a graph that is greater than 0, aka we would say it's above the x-axis in those intervals of x. Perfect. Now, again, case 1 and 2, it depends on if it's greater than 0 or less than 0, or even equals to in here, because if it was equals to rather than just a strict inequality, these dots would have been filled in on these ones here. So we got to be very careful, depending on what the original sign is. Our end sign should follow the exact same form, and that our solution should be a strict inequality rather than an equals. But I can't guarantee which form you might see. Okay, there's a case analysis of the same inequality that we dealt with above. So now we have 3 different methods which we could approach it with. One is the graphical method, which is non-algebraic. We then have our first algebraic method, which was the root and test point / sign analysis, which are relatively the same. And then lastly, we have our method 3, which was the case analysis. Okay, now here's where the application comes in. Let's suppose we were given this problem. A golfer hits a ball down the fairway, and she would like to know the length of time in seconds that the golf ball was at a height of at least 25. This is where we should highlight this information. As soon as you see key terminology like that, especially in the inequalities unit, I want you to arrow down to this and be like, when they use the keyword at least, this means we must be talking about where it's greater than or equal to, because at least means 25 is the bare minimum she's looking for, and then she's looking for obviously the values that include the above. So how long is this golf ball in the air for at least 25 meters in the air? A function that describes the height of the ball versus the time is y is equal to negative 8x squared plus 40x, where we know if the a value is negative, this is a downwards facing parabola. So this is good. It matches up to our expectations of what, any sort of tossed ball in the air would be, or any hit ball through the air. This could be a baseball, it could be a golf ball, a football. All of them would follow a negative trajectory like that. Now, we want to write an inequality in terms of one variable that describes this situation. Here's what it's going to look like. We're going to write out that we were given a function that represents the parabola. So let's start off by writing our negative 8x squared plus 40x. That was the point they gave us. So this parabola follows this trajectory, but we want to figure out where it is at least the 25, meaning it must be greater than or equal to a value for y of 25. Now, of course, we didn't want to leave it like this. This is never the way we left our one variable inequalities. We always wanted to isolate them to 0. So realistically, I guess we could leave it here depending on the situation. But for the most part, I told us in class, we want to isolate this so that one side is 0. To do that, I'm going to minus 25 from both sides. And I'm going to get that we have negative 8x. And I'm going to do this all in one color here. We have negative 8x squared plus 40x minus 25 is greater than or equal to 0. We don't flip the inequality symbol. When we move the term across, unless we're dividing or multiplying by a negative, this will be the direction in which the inequality faces with 0 on the right-hand side. So here's our inequality in one variable, aka x is the only variable we see that describes this situation where it must be greater than or equal to 25, or it's flying in the air at least 25 meters above the air. Okay. So there's our first part. Determine how many seconds the ball was at a height of at least 25 meters. To do this, I'm going to recommend that in these sorts of application problems, if you take a look at this, normally we would want to factor this, right? That's our whole goal of these. We see a trinomial, whether it be chapter 0 or 1 or 2, we wanted to factor these things. But in order to factor this, we have to look at this and say, hey, you know what? I don't know if we can factor this using nice numbers. What multiplies to make negative 8 times negative 25 and adds to make 40? I mean, I don't know about you, but I would be lost right away with this. So what I want you to do at this point is I want you to use quadratic formula. And so what we're going to do is we're going to use quadratic formula in this specific section here. And I mean, the indication you should use quad formula is kind of within the problem itself. They say determine the answer and round to the nearest tenth of a second. As soon as they say anything about rounding, you're probably not going to factor this unless it ended up being some sort of really nice fraction. Okay, let's plug this in here. So our A value was negative 8 from above. Our B value was the middle value. If we scroll back up, we notice it was positive 40. And then our C value was equal to the negative 25 that we brought over. Perfect. Now that we have an A, B, and C, we can plug them into quad formula. If you don't know what quad formula is, it's going to be on your formula sheet, so no reason to memorize it. It's negative b plus or minus the square root of b squared minus 4 times a and c all over 2a. Okay, plugging in the values here, we get x is equal to negative b, which is the negative 40, plus or minus the square root of 40 squared. And then we're going to go minus 4 times a, which is negative 8, times c, which is negative 25. Perfect. All divided by 2 times the a value, which is 2 times negative 8. Excellent. So now we're going to get x is equal to, when we simplify this, we get negative 40 plus or minus. Let's do this one in our calculator here. We're going to go back to the main menu, go second, the root key. We're going to go 40 squared minus negative 4, and not negative 4, but minus 4 times negative 8 times negative 25. And then we're going to end up getting that this is 28.28. So realistically, as long as we hold on to a tenth, we're okay with that, 28.28. And then this is all divided by negative 16. And then when I plug this into the calculator in terms of the plus or minus versions, let's actually do this together and get the two x values. So our first x value, when we do the positive case, let's put it in a fraction. It's negative 40. We're going to add 28.28, and then we're going to divide it by the negative 16. When we do this, we end up getting our first x value is 0.7325, and that's not too many decimals to hold on to. Our other option is going to be x is equal to, we're going to plug this in exactly the same way, so we can go up and copy it, but I want to go back and I want to change this from a positive to a negative value. When we change it to a negative value, we end up getting that x is equal to 4.2675. Okay, we now have two different x values that represent the different times. Now, to think about this logically, what's actually happening, and it might even be important just to draw out a very simple graph of this, not anything super complex, just a basic graph, which I'll draw above here. we think about this in terms of time won't be negative. So maybe I'll just draw the quadrant 1. I'm going to draw it like this. And then what I'm going to do is I'm going to sketch in the following. One of our x-intercepts was here. The other one was about 4. The value of this one was 0.7325. The value of this one was 4.2675. And our parabola should look kind of something like where it's going to start at 0, 0 because it's a golfer on the ground. If we look at this inequality here, the inequality is, or the function is defined all in terms of x. If x equals 0, the whole thing goes away, meaning if there's 0 time, there's also 0 height. The person should be hitting it from the origin. So we're going to scroll down and put a point on the origin. And then what I'm going to do is just draw a simple parabola that goes up and then comes back down somewhere over here. Now, we don't really know in terms of what it is, whether it has certain x-intercepts or whatever in terms of the, in terms of this piece here. But actually what we can do is, I should backpedal this here, because we know that this graph is solving for the x-intercepts because of the way we set up the inequality, it actually rises and falls such as this here. So our inequality, and we could plot this out if we really wanted to. If we wanted to type this into our graphing calculator, not that, on an algebraic approach we should, but I'm going to type this in as negative 8x squared, and then plus 40x, and then minus 25. When we graph it, here's our graph. It rises and falls through those two x-intercepts because of the way it is. So it's not going to be at the origin. It actually has this parabolic shape that we've predicted here. I'm going to just have it cross through, go up, and then come back down. There we go. There's our rough parabola. How much time does it spend at least 25 meters in the air? It's the x values that are contained between those 2 points, including those 2 points. So we're going to put a solid dot here representing the one x-intercept, a solid dot over here. All of the x values that are between this represent the total time that it takes. So when we summarize this, we're going to say, therefore, the time the ball is 25 meters or higher is from a lower bound of 0.7325 and then between the 4.2675. Now, they said to the nearest tenth, right? So I should be answering this to the nearest tenth, which I'll do. For the first one, it's going to be 0.7. For the second one, it will be 4.3. What is the total time in the air? We're just going to subtract these two values from each other. So on the main menu, I'm going to take this value. I'm going to subtract my other value, which is 0.7325, that is, and I get that the ball was in the air above 25 meters or at least 25 meters in the air for 3.5 seconds. So let's just write out that subtraction just so we can see it. The inequality of it being in the air is represented by this piece, and then the specific time is actually represented by 4.2675 minus 0.7325, which is equal to 3.5 seconds. There we go. So I like to include the inequality in the answer like this purely because the inequality is representing where it belongs, 25 meters or higher in the air. And then again, with these problems, if it doesn't factor right away, use quadratic formula. Quadratic formula is your best friend. Make use of it. It's there for you. It is considered to be algebraic, so do not fear using it to help you solve problems, because I think it's a great way to think about solving these problems in an algebraic approach, especially when the numbers are a little more difficult.